Quantum Foam. Episode 19. Loop Quantum Gravity.
Quantum Foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
so we are going to take a look at this loop quantum gravity, and this is episode 19 of Quantum Foam. Presiding is myself. I don't work for you. I don't work for him. I don't work for them. I do work for me. I am a single voice with only my opinions and only the regurgitation that I offer you and that I authorize you to be able to hear by me pushing this record button and you hearing it. And so let's get into this. Without further ado, we can deal with the issues surrounding why I was procrastinating this entire time later. We all know that this is a very complicated topic. In a way, the string theory topic was quite complicated.
There are many more topics we need to get to. We have to become proficient at some point. Let's keep on researching.
This other topic of loop quantum gravity is our other method and our other candidate, another popular candidate for the theory of everything. This one is a little bit less understood. It is going to take possibly a little bit more time to figure out what the fuck this shit is. So we get into this right now. All right, we are taking a look at this newish theory of loop quantum gravity, and it's really not a theory, it's more of a method. Loop quantum gravity, and a different approach to an attempt to calculate space-time around us. Loop quantum gravity, loop quantum gravity, loop quantum gravity, loop quantum gravity. So what is this? They always like to say things like, it's the only game in town. String theory is the only game in town. Loop quantum gravity is the only game in town. So what if there is another game in town? Let's take a look at this loop quantum gravity. Obviously, it's a theory of quantum gravity. It's another game in town. According to this, it's another theory, another method for calculating and describing quantum gravity. If it wasn't possible before, now it is. It is now possible.
Oh, great.
One main idea with this is they say that general relativity does, in fact, necessitate a background-independent description of space-time. But does it? I think it probably does. We need a background-independent description of reality in order to be as accurate as possible, more than likely. According to loop quantum gravity, it says yes. More than likely, more than likely, more than likely, more than likely. You do have to have a background-independent grid of math to describe reality. So there are different things like, what is our Newtonian G? There is obviously an accepted constant that is our Newtonian gravity constant. Big G is Newton's gravity constant. So keep that in mind when we're talking about big G here. Everybody knows what big G is.
I don't think everyone knows. I seriously don't think people know what it is.
Yeah, it's probably a good idea if you tell them.
My Newtonian constant of gravitation, big G, is equal to 6.674 times 10 to the negative 11th power, meters cubed over kilogram seconds per second, or Newton meters squared over kilogram squared. Remember that 1 Newton is a force unit and it is equal to the amount of force needed to move a 1 kilogram box exactly 1 linear meter per second, every second of time.
So there are several ways to write it, and tell them another one.
1 equals 1 kilogram per second. The force of about 175 pounds, maybe the weight of an average adult male, is equal to about 780 newtons on the ground of the Earth at sea level, or most places on Earth really. It takes into account small g, negative 9.8 meters per second squared, the force due to the Earth's gravity that is exerted on every portion of mass on Earth. Everything, you, me, the table, your car, etc.
I'm a big G. You're a big G. Everybody is a big fucking G if they know what they're talking about. I'm a big G. I'm a big G. I'm a big G. I'm a big G. Quantum gravity. Newton's gravity. This big G is Newton's gravity. Okay, so what is this? Well, it's a conservative vector field when it interacts with the stuff that we're doing. It describes space-time differently. What makes this loop quantum gravity different from other previous approaches and different from string theory and different from other accepted conformal theories is it describes space-time with connections instead of our regular Cartesian style coordinates. That's point-particle coordinates. Every point is a coordinate on some big, grand, huge lattice of space-time. So string theory necessitates background dependency. It is dependent on a box grid with 11 dimensions, supergravity, in order to describe it. So essentially, if you had a math box of your string theory, it could float through a loop quantum gravity described area of space-time, a loop quantum gravity position of space-time. So essentially, you could have both of these theories and wave them right on top of one another, and they would not interact in any way, shape, or form, because one of them is dependent on a math box, which essentially can be thought of as a theoretical description, and the loop quantum gravity can be thought of as another theoretical description. So we don't know which one's right. We don't know if they really would interact or not. We assume they would not. They probably would not. That is sort of just to describe the differences between this theory and another theory, this method and another theory. What exactly does this theory rely on? We're going to get into that right now. Loop quantum gravity. This theory relies on connections between space-time, connections of space-time between space-time quanta. The most important aspect is it relies on connections between one another. Essentially, you're looking at a region of space-time and then writing up a perturbative method to examine this. What are these things called? They're spinors. It's like a description of a spin and a position and an angular momentum and a vector. That is a vector that includes the spin of said particle or region of what you're describing. You have your vector of spin. You have your other connections of space-time between another part of space-time. And what these can be described as are loops. Each of these are a section of space-time that is really a loop. And so these are Ashtekar variables. And so Abe Ashtekar is a very important figure for loop quantum gravity because in the 80s, in the 1980s, he released some new papers that deal with this theory. Asymptotic quantization, 87. New perspectives in canonical gravity, 88. Conceptual problems of quantum gravity, 88. And there's more too. So a little bit more about what exactly these variables are and why this was necessary to do before any methodology or theory like loop quantum gravity could come to fruition. He was one of the people who helped create what they call an ADM formalism of general relativity, obviously named for the authors Richard Arnold, Stanley Deeser, and Charles Misner. You've heard a lot about Misner, I'm sure. Not sure about the other guys. We have spoken about these so-called Hamiltonians, which this is essentially an equivalent but more abstract reformulation of some theory, of probably a classical mechanical theory. It's added to the formulation of statistical mechanics and quantum mechanics as a whole. So that's the half of the Schrödinger equation or the half of the Dirac equation. The Hamiltonian is the goods in the box. So this ADM formalism, it itself is a Hamiltonian formulation of general relativity. And this plays a very important role in these canonical quantum gravities, these theories of so-called canonical quantum gravity. You could say, according to canon law, this goes back to the Roman Church and marriage. It could be described as being cardinal. It is the accepted law. So dealing with these canonical quantum gravities that they are coming up with, this ADM formalism was an important precursor to loop quantum gravity. In the ADM formulation of general relativity, space-time can be thought of as being split into spatial slices on a time axis. That's a little bit different than what might have been done earlier last century. But these now can be referred to as Ashtekar variables from Abe Ashtekar. He basically introduced a new set of canonical variables. And so these things can represent in a different way three-dimensional space. It's sort of an unusual way to describe spatial slices of three-dimensional space. And this deals with the SU2 gauge field, and it's a variable, these Ashtekar variables. These gauge theories, remember, it's one where a Lagrangian does not change under local transformations from certain Lie groups. Essentially, they don't apply a Lagrangian to it, so they're not messing around with Lagrangians for the gauge theory because it doesn't change. They don't want it to change in these. Abe Ashtekar, he is one of the founders of loop quantum gravity. This was an important step that needed to be done before loop quantum gravity and loop quantum cosmology could be further explained by other people. He has a bunch of descriptions, his own personal takes on loop quantum gravity, and he has written them for non-physicists to be able to understand.
That is an important skill to have. I'm glad you guys are doing this for others. People need an abundance of capable teachers. The internet is full of dumbass retards reading shit from a slide and making YouTube videos trying to explain a lot of this complicated science. Most of them are full of shit and don't understand a damn thing about what they are trying to talk about.
These guys, back at the end of the century, at the end of the millennium in 99, they were able to calculate the entropy of a black hole, and we're going to revisit this black hole entropy. It's a very important point as it deals with this loop quantum gravity because various things. We'll get into that. This calculation Abe Ashtekar had done for black hole entropy, it matches the legendary 1974 prediction by Stephen Hawking himself.
I was very pleased to hear that they had done this. Remember, this was my thesis and where my journey began in contributing to science as we know it.
Yes, we know. Hawking radiation, particles that are emitted from black holes.
So Roger Penrose, obviously he's pretty famous, Oxford mathematician, he described Abe Ashtekar's approach to quantum gravity as the most important of all the attempts at quantizing general relativity. So we'll get into more people and more individuals that are very important, but he is definitely one of them. Carlo Rovelli, Lee Smolin, and Sabine Hossenfelder. Dr. Hossenfelder, all doctors. We'll get into some of the descriptions by these individuals in a bit. So for now, we understand what these Ashtekar variables might be, and they were formulated a long time ago. This is work that they did in the 1980s. So different things that you can describe with these within the methodology and theory of loop quantum gravity. There are open loops, closed loops. What describes how they described it? These closed loops are actually closed circuits of gravitational functions or gravity functions. You take a look at your particle, then you break it apart. It really is your loop. Those loops essentially can be looked at like a ring or a torus shape, three-dimensional torus shape. Let's go back into the spinors, which essentially are the vectors that include the spin. They describe the connections between the quanta of space-time, which essentially are these loops and these Ashtekar variables. Moving into more updated understandings of this theory. Carlo Rovelli wrote that paper about 20-something years ago, 20-something pages long. So he sort of is one of the main founders as well of loop quantum gravity, and Lee Smolin has been a part of that school of thought for a long time as well, in addition to making advancements in string theory. Most of these guys probably have made advancements in all sides of physics, so don't be surprised if they have contributions to string theory as well as loop quantum gravity. But what we are talking about here is loop quantum gravity, and that is what is important here. These guys are describing gravity with particles that are actually closed loops. They're describing general relativity. They are trying to describe general relativity in a way that can be extended down to the size of Planck scales and other quantum phenomena, because what we are really looking for here is a theory of everything. That means we need to reconcile general relativity with the stuff that we know and the various theories of quantum gravity. What we're trying to do here is describe general relativity possibly using ADM formulations of general relativity. So they're saying these masses are zero. The graviton mass is zero. It's massless. It has a spin too. We'll get into the intricacies of the spin at a later time, but right now we are going to get into some material that is more relevant to our topic this episode, and we will get to some of that other stuff next time. Also, what we're dealing with here is the variance and the covariance, and how general relativity and all physics and all physical laws are in fact the same.
A quick example of the difference between variance and covariance is as follows. The variance can be used to describe the volatility of a stock price and how far it can travel away from a mean share price. A covariance can measure how two random variables will change when compared to one another, such as the possible returns of two separate company stocks.
We're trying to describe physical laws that are the same in one framework that describes everything. To do this, we're using the methodology of loop quantum gravity, which deals with the spins, the spin networks, and the descriptions of sections and quanta of space-time as a whole, instead of Cartesian point particle descriptions of just space as matched together with a variable of time.
Hey, it's break time.
All right, we are about halfway through
Episode 19, Loop Quantum Gravity,
of Quantum Foam.
So these spin networks result in a 3D space. We're trying to describe a 3D space as it is. This brings together an idea of isomorphism. You might have heard me say something being isomorphic. This just means it is differentiable along the manifold that we're speaking of. Isomorphism is just a description of a differentiable manifold. It doesn't require supersymmetry, or any extra dimensions, or a background dependency. The goal of loop quantum gravity and the theory that is, it doesn't require supersymmetry, it doesn't require a million dimensions, and most importantly, it does not require a background that is dependent on there being a background. So, describing the connections between space-time and space-time is the way we are going about this, instead of describing space with a background-dependent lattice and then comparing it with a time variable. That's not how we're doing it here. So now we get into this Bekenstein-Hawking equation and how it relates with black hole entropy, because black hole entropy and the physics of black holes is still a misunderstood. Black hole entropy is a understood. The fuck do you say that? Black hole entropy. Black hole entropy. Black hole entropy. Black hole entropy is a scarcely understood area of physics currently. This deals with our loop quantum gravity. We are interested in these black holes and the math and physics surrounding them because there might be a way to detect what is actually inside of the black holes, the entropy inside the black holes, with more than just your mass of the black hole, your electric charge of the black hole, and your angular momentum. That's what we are hoping for. That is a possible way that we will be able to test these theories of loop quantum gravity. It's very important to breach upon what exactly these fucking black holes are and what this entropy shit is and these formulas and how this matters, because there may not be any other way to test this stuff. So right now there are a few ways, and there are various groups around the world attempting to work out a way to test whether or not loop quantum gravity has any more merit than string theory. As soon as some of these tests come in for this theory or any of the others, there will probably be a flood of breakthroughs in both or all theories. And that is sort of what we are looking at here. That is why I'm doing what I'm doing. That is why they're doing what they're doing. Hopefully somebody hears something in the right way that makes them want to go out, be motivated, and study physics in a way that hasn't been done before, that they might be able to understand something that has been missed by everybody in the past.
Hell yeah. I wish I had the tech you guys have now. I would have had a hell of a heyday.
So this Hawking-Bekenstein equation, or Bekenstein-Hawking equation, or just call it a Beck-Hawk entropy. That might be how I refer to it. So this Beck-Hawk entropy, it is a window into the hidden quantum gravity that we're trying to be able to measure so that we can have a better understanding of quantum gravity, and we can test whether or not certain areas of these theories really do describe reality or not, one way or the other. Even if they don't, we would like to know if they don't. Revisiting the spin networks, it's essentially a diagram representing a particle or a quantum or area of quanta or a field. It describes the states, the interactions that happen through means of mathematics. We're describing these interactions with a complicated subset of mathematics that we will get into at a later date.
But these spin networks are of a certain interest.
Now, these Beck-Hawk entropies, it's a window into the quantum gravity. All they can do now is measure the mass, the electric charge, and the angular momentum, which is essentially the mass, the velocity, and the radius. We get into some other concepts as well. We're not going to go too far into this. Some of these things need to be understood for the purpose of understanding what it is that loop quantum gravity is trying to do. There is your Planck-Dirac constant, your h with a dash on it. That just means h, your Planck constant, over your spin, 2 pi. So,
right, we are talking about energy here. The Planck constant is about 6.626 times 10 to the negative 34th power joules per second. A joule of energy is the amount of work needed to move 1 Newton meter, or also you can refer to electron volts and accelerators, but we won't get into that for now.
Black hole event horizons, they can't increase. They don't seem to increase. We have not viewed them to increase by themselves, so to speak.
Only when more matter goes inside the black holes do the 3 known values you mentioned earlier have the ability to change.
The entropy within doesn't appear like it can increase the event horizon size of the black hole. However, they do increase with transformations.
Indeed.
That is right, sir.
When there is a set transformation, then it increases. This behavior is reminiscent of the thermodynamic entropy of a closed system, because if it's the same, then we can look at black hole entropy the same. It's a monotonic function of area. What is this? It's a function that helps you understand the specifics of a certain black hole that we can observe and view with a telescope. The different kinds of black holes you may have heard of. There's the Schwarzschild black hole. This just means it's a black hole that is spherically symmetric and stationary. So it really depends on what type of black hole you're referring to. There's the Schwarzschild metric. We're talking about Schwarzschild black holes. Then there is another one that is the Kerr-Newman metric. This is a black hole that is spherical or round and rotating, but it is a different subset of a description describing a black hole. Big G is obviously your Newton's gravity constant.
Big G.
What we're really doing here is they are attempting to come up with theories that can describe quantum gravity, and we are looking in black holes to see if we can measure anything from potentially another universe. There may be information hidden within the black holes from another universe that would tell us that other universes are possible, and the connection between one universe and another is possible. This also includes the possibility of a connection from one universe to itself again. So a spinning black hole may actually create a wormhole to the same universe in a different position in space-time within our universe, within this universe that we're in. This so far has not been done. According to Carlo Rovelli himself, the mathematics of a white hole should essentially be the negative inverted math of a black hole. It is very important that we understand these black holes, because what is on the other side of the black hole? Is it a white hole? Are these black holes actually white holes that are on the other side of another black hole in some other space-time or some other universe? This is information that would likely cause quantum leaps in our understandings of quantum gravity and coming up with new theories of quantum gravity. We understand a little bit about these Bekenstein-Hawking equations, how it deals with black hole entropy. There are other ways to describe these canonical laws that we accept. Remember, we spoke about Poisson's equation and the Laplacian equation and such?
Right. Lagrangians, functions that describe a physical system. Laplacians, effects done to a math lattice box that is of interest to us. And also the techniques of applying Gaussian functions. We know what's up, playa.
Hey, I'm supposed to be the sounding board for these 10 episodes. No fair.
Relax, guys. I can use all the help I can get. You can take turns. It don't matter to me. Some of them may not be using Laplacian mathematics to describe their space-time lattices. They do use something called a Poisson's bracket, and they use that to fully describe their quote-unquote Hamiltonian, which is half of our Dirac equation in quantum mechanics that can describe our quantum gravity. there is still a time problem. I understand how to get around our time problem, but remember, there is still a time problem that is present in this theory, in all theories in general. Properly understanding how to deal with your time is probably the most important thing you can do in studying physics, because string theory treats time differently than space, and general relativity treats space-time the same, or it dictates that that's the way you should do it. And so the independence of the background and loop quantum gravity itself also states this. The main thing about this is that you need to treat space-time the same. Time is not any different than space. Space is not any different than time. However, we know there is something different because there are 3 spatial dimensions and only 1 of time. We cannot fathom the variable of time the same as the variables of space, simply because we are individuals that live in 3 space, and the passage of time is a linear, forward-moving variable that we scarcely understand. So one problem with this theory and experimental evidence that possibly can be said to not support this theory came about in 2009. There were some gamma ray bursts, and if we are to describe space as loopy space, sections of loopy space, then there should be a difference of gamma rays moving slightly below the speed of light that go through this loopy space. However, what we see to a high degree of accuracy is absolutely no difference. So this is not good for the theory of loop quantum gravity. However, it just may be something that we don't quite understand fully, and it may be irrelevant. Keep in mind, that is why we are studying this. That is why we are looking at different theories of quantum gravity. There are irrelevant, possibly more than even 1 or 2. There are even more possible methods to describe our quantum gravity. As with all things, we need to take a look at the most popular, meaning the most physicists that think that it might be the correct theory. So we got our string theory, we got our loop quantum gravity, what we're describing here. There are several others.
Asymptotically safe gravity. Asymptotically safe gravity. Asymptotically safe gravity.
And then causal
Dynamical triangulation. Causal dynamical triangulation. Causal dynamical triangulation.
and then taken as a whole, any other emergent theories of gravity that isn't necessarily a specific theory, but a class of approaches. This is a lot of the stuff coming from
Sabine Hossenfelder.
She is a little bit younger and possibly more willing to piss more people off in the name of studying science, because if you're 70 years old and you come up with these theories and you say that's the way it is, that's just the way people are. So here we are, 30, 40 years old. It's our time now to attempt to describe what the fuck is going on, because everybody can't be right, and more than likely everybody is right a little bit and wrong a little bit as well. So what we need to do is find out the correct parts of the theory and make sure that that makes it to the next theory. This asymptotically safe gravity, Steven Weinberg from 76. It just applies the idea of asymptotic safety to gravity. It can solve the problem of quantum gravity, but it hasn't been proven either, just like these other ones. So causal dynamical triangulation, there are problems with infinities. That's a big problem with a lot of the math that describes a lot of these theories of quantum gravity. Most theories rely on removing these short little distances so that they are finite extensions instead of infinite extensions. Loop quantum gravity works the same way. So does string theory, actually. That relies on removing these small distances, and so the so-called triangulation, the finite size of triangles, is a mathematical aid, and one that eventually takes the limit where this size goes to 0. So essentially they're saying the stuff is 0. The major problem with this one is we're unconvinced of this causal dynamical triangulation because it does actually treat space and time differently. Supposedly Einstein taught us not to do this. Even if Einstein is wrong in general, it's not that he is wrong, it's that he didn't have the whole picture. That's probably right to treat them the same, because it seems like there are a lot of things that they are the way they are. Otherwise, we would want to treat them differently. But I believe, as does most everybody else, that you need to treat space and time the same. These emergent gravity theories, that's just saying that these are approaches that say quantizing gravity doesn't make sense when you really think about it. That might not even be what we need to do. So instead, one removes the inconsistencies between the gravity and quantum mechanics and say that's not exactly what you do first, and that's not the point of the new theory, so to speak. The theory of everything wouldn't do this. We don't know this. We think it might. So a lot of stuff to think about here, a lot of things that we can go further into detail with. There are a lot of important people people in this field of study: Carlo Rovelli, Lee Smolin, Abbe Ashtekar, Sabine Holzenfelder, Frau Holzenfelder. And it just so happens she's German, I can speak German, so that's kind of cool. So what else can we do?
Probably just reiterate the main ideas so that we have a good foundation to continue our course of study here.
So the main idea is that you look at space-time as chunks, and the space-time lattice, as Carlo Rovelli likes to demonstrate to non-scientists, is a blue piece of fabric, like a 1.5 by 1.5 blue piece of fabric, and your electromagnetic field is a yellow piece of fabric, and they just lay right on top of each other. And so they both can move, they are both made of constituents, and potentially this new description of space-time as a interconnected network of quanta might be closer to the theory of everything than people think. I think potentially if you mix string theory and loop quantum gravity together, adjust a few variables, take out some bullshit, and formulate a new picture with all of the correct math, this actually can be your theory of everything right now. So we are fastly approaching a theory of everything, and in order to do so, we need to understand what this stuff is. So last time was string theory, this time is loop quantum gravity, and next time, episode 20, will be quantum mechanics. And we will take a look at our quantum mechanics, possibly our quantum electrodynamics, and possibly our quantum chromodynamics, and other such methods of dealing with quantum math. And so that is it for this time around, episode 19 of Quantum Foam.
Quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.